didn't bring my phone. Is it now time?
Oh.
Close enough? Oh, it's close enough. Okay. No, it's fine. You can use it. Whatever. Okay, so just notation. We have natural numbers. Integers contain natural numbers, negatives, and zero. Real numbers, complexes. These magical symbol, the universal quantifier for every, and then there exists, which also means there is at least one or some elements, and then the element sign, which will often look like my epsilon, and so life is hard. And then I almost always write the tilde for the negation, but in most books you see this kind of long bar short thing. It means not, so not true is false. And then and or, it's common to use those. We worked on the difference between contrapositive, not Q implies not P, so these are logically equivalent. And then the converse, Q implies P, its converse would be, its converse, Q implies P is the converse of P implies Q. Thank you, I was wondering why I was crazy. And then we have different types of proofs, direct, contrapositive, exhaustion, induction, and we were working on strong induction when we left off. And then the key thing with induction is you have a statement about the natural numbers. Nominally, you can start at 1, but it doesn't matter. You can start at minus 406 and go forward. You can start at 209 and go forward. Okay, so you can start at any base case you want. So you prove a base case is true, and then for natural numbers greater than the base case, prove that the statement P of K being true implies the next one is true. That's induction. And magically, you get an infinite number of things that are true from the base case onward. Then we have this equivalent thing called strong induction, or the second principle of induction, where it allows you to organize the proof in a slightly different way. Sometimes it's more convenient. It's logically equivalent. And in that one, you have this statement, and you have a base case, but the induction step is you say, everything from K back to the base case, all of those statements being true implies the next one, K plus 1 is true. Then you get everything is true. And then the point is, this is ordinary induction if you modify your statement to be some other logical statement indexed by the natural numbers where it has the and of everything up to the nth one. Okay. This is exactly what we said here. P of j is true for all of these. That means the and is true. Okay. So P of k implies P of k plus 1 would be there. Questions? We're good.
So my question, is induction a type of proof by exhaustion, or is it like it's...
No, proof by exhaustion is really like the 4-color problem. You eliminate something to, I don't know, 400,000 different cases, what a human could never check, but then you let a computer, for example, check every single one of them. That's a proof by exhaustion. Yep. So it's getting a finite number of cases and just checking every one of them. That's a proof by exhaustion. Okay, so then we were going to apply this to the fundamental theorem of arithmetic. There we're using the notion of composite numbers and primes. And once again, this course doesn't really care about that, but it's easy to make statements about numbers that you guys understand, the integers. Okay, and so a number is composite when you can write it as a product of smaller integers. And it has to be bigger than 2. That way you can't just go 1 times 1 times 1 times 7. Hey, that's a product. No, it's not. Okay? And so and then if you can't write it, if you cannot write it as a product of smaller natural numbers, then the number is prime. So 1, 3, 5, 7, 11, etc. Okay, so the fundamental theorem of arithmetic is that every natural number bigger than or equal to 2 can be written as the product of 1 or more primes. So we're going to do that by strong induction. And so the way we'll organize that, this is where we left off. And this is where the bad handwriting starts, okay? Because I'm doing it standing up. See if that helps a little bit. We're going to write it as, what is our statement? P of n is that if n is greater than or equal to 2, then n can be expressed as a product of 1 or more primes. Okay, so that's our statement. And then our base case is, we're going to start at P of 2, okay, because the theorem starts at 2. So our base case will be P of 2, and then 2 is the product of 1 or more primes because 2 itself is prime. Okay, so P of 2 is true. True. Because 2 is prime. Okay, so the product of 1 or more primes. So all the prime numbers will be only a product of 1 prime. Okay, it's not really a product, it's just, that's how it's stated. Okay, so the base case is simple. What's the induction step? Then you'll see what's nice about strong induction, okay? So you want to have k bigger than, so, excuse me. So we assume now that for 2 less than or equal to j less than or equal to k, P of k is true. And just to be clear, what do we have to show? Yeah, it's P of j. Yep. To show is that P of k plus 1 is true. And please, when I make these mistakes, it's great. Call it out, okay? The sooner the better. It was so embarrassing on Tuesday when I got about 5 minutes in and I had my 2's and my k's all messed up on that, okay? But fortunately, most of you came back. You didn't hold it against me. You didn't have a grudge. That's very nice of you. Okay, so now why would induction ordinary induction not help very much? Suppose k plus 1 is 11. I know then k is 10. Knowing that 10 can be written as a product of primes, how does that help me with 11? Not a lot of help, okay? If this were 18, the previous one would be 17. Just knowing that 17 can be written as it is a prime doesn't help me to factor 18, you see? But if I reach back, you'll see what happens, okay? So, we have 2 cases here to show this. So this is now, proof by exhaustion, we enumerate all the cases, but there's only two, so it's not very exhausting, okay? So it's not very exhausting. There's two cases. K plus 1 is either prime or composite. Okay, so case 1, K plus 1 is a prime number, okay? So it's prime. This case is trivial because if K plus 1 is prime, then this statement is true. It can be written as the product of 1 prime, okay? Then P of K plus 1 is trivially true. Okay. Now the second case, K plus 1 is composite. Okay, so here we now use the definition of composite. Okay? It's the only thing we have going for us. Whoops. Hence, there exist A and B natural numbers such that K plus 1 is equal to the product and these natural numbers are bigger than or equal to 2 and less than or equal to K. Okay, so that's the definition of composite. I can write it as natural numbers that are bigger than or equal to 2 and smaller than K plus 1. So that would be K.
Does it have to be K or K plus 1 on the right side of the...
It's K. Here's composite. N is composite if we have N minus 1. Okay, so now A and B are composite. Okay, A and B are natural numbers, and we know our assumption is that for any natural number between 2 and K, we can write them as a product of primes. That's what strong induction allows us to go back to all the things that preceded K plus 1. Okay, so hence, there exist primes such that A equals P1, P2, dot, dot, who knows, PL. B equals, say, Q1, Q2, dot, 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 I don't know, M. Okay, so we get this by the induction hypothesis with strong induction. We get to search back through all of those. And so therefore, K plus 1 equals A times B equals P1 to PL, Q1 to QM is a product of one or more primes. We'll leave out the one or more. Bingo. And that's it. Questions?
So it's not necessary for us to consider two cases again when it comes to A and B. We just have to say B1, B2.
Yeah, because the definition of composite says I can write it as a product of two natural numbers that lie between 2 and then n minus 1. That's the definition. Now, if it can be written as 3 of them, it's still composite because you multiply the first 2 and you keep so you don't have, you just apply the definition, and that's how we've written it. We could have said it's composite if there exist 2 or more numbers, but we didn't bother with that. This is much easier. Okay, other questions? Cool. And then once again, if you wanted to do this with ordinary induction, your P of n would have said for every integer k between 2 and n, I can write it as a product of primes, okay? Not just that n can be written as a product of primes, but every one between 2 and this number. That would be the and of those. That would be the P tilde to do ordinary induction. So you can go back and rewrite those, and it just depends on the problem which one is easiest to use. Wow, looks like we did it right. Okay, so now we're going to do the thing that drives students crazy initially, but then after a little while you come to love it. It's called proof by contradiction. Okay, so when you've been taught them in the past, you didn't get enough information to get the logic of them. So we're going to do proof by contradiction. The problem is, for some of you, proof by contradiction sounds like proof by being illogical, okay? It's not true. It is totally logical. So what is a contradiction? Okay? A contradiction is a logical statement that is both true and false. Okay? It's not possible. It's impossible. We have binary logic. It's either true or false. So this can't be, this cannot be. Okay, so now you're going, huh? This is hurting me. So let R be a logical statement. R and not R true is a contradiction. Okay, R can only be false or true. It cannot be both. So if this statement is true, then R is both true and false, which is a contradiction. Okay, so if you can organize your thoughts in such a way that you can prove that something is true and false, you've arrived at a contradiction. So, here's an example. R. M and N are natural numbers and have no common factors, okay? M and N are even is a contradiction of M and N have no common factors. That's a contradiction. okay? So you would have both R. This is not R, okay? M and N, that implies not R. They have a common factor because 2 is a common factor. So this is how Euclid organized his famous proof to establish that irrational numbers exist. Okay? So we're going to use Euclid's proof to show square root of 2 is irrational. Remember the Greeks? They just wanted everything to be so beautiful. They had 1, 2, 3, 4. They understood 1 loaf of bread, a half loaf of bread, a third of a loaf of bread, 2/3 and 1/3. They understood fractions, and they thought everything was either an integer or a fraction, rational numbers. That was rational to them. That was logic. That was beauty. And then when someone claims there exist things that are not like that, and they got that by studying 1 at a right angle and measuring this length, okay? That's the square root of 2, okay? They go, that's irrational, it can't be true, okay? That formula cannot be true. Then Euclid proves square root of 2 is not a rational number, it's irrational. So let's see how he did it, okay? So Euclid's famous proof that square root of 2 is irrational. Okay, how much more beautiful can it get than that? So, here's our statement, P. Square root of 2 is irrational. Not P would be square root of 2 is rational. So, our strategy is we assume not P. We're going to arrive at a contradiction. Hence, not P has to be false. Okay? True statements cannot lead to contradictions. That's how logic works. Okay? False statements can lead to anything. We understand that, okay, in this day and age, okay? False statements can lead to anything. So we're going to assume not P, square root of 2 is rational, and deduce that that is false, and hence P is true, okay? We'll show not P leads to a contradiction and hence not P must be false. Conclusion, P is true. So that's exactly what Euclid did. So how did he organize his argument to show that assuming it's rational, I can lead to something illogical like a statement that is both true and false? Okay, so what do we know about rational numbers? Oops, I wanted this to be blue. I don't know why, but I did. If square root of 2 is rational, there exist integers. There exist m and n natural numbers such that two things are true. I'm going to call the first one R1. M and N have no common factors. Okay, and then R2 would be that square root of 2 is equal to M over N. Let me put N not equal to 0 here. Just, oh, N doesn't have 0. Ha ha, I don't have to do that. Yes. Okay, natural numbers, they start at 1, so M over N. Okay, so from R2, if this statement is true and I square both sides, what do I get? I get 2 equals M squared over N squared, right? So R2 implies 2 equals M squared over N squared. And that implies that 2 times N squared is equal to M squared. Right? I multiplied both sides by N squared. So I'm using, the things I'm doing now are not part of my hypotheses, they're part of the rules of how arithmetic works. Those are other theorems that are true. This being equal, I square both sides, they stay equal. This being equal, I multiply both sides by N squared, it stays equal, okay? That's the other rules of logic and known theorems that I mentioned before. So, if M squared is even, what do we know about M? That was Tuesday's lecture, okay? So this implies M squared even, which implies M is even, okay? So this was done Tuesday, one of our nice proofs there. Okay, so now, if M is even, M even implies there exists some natural number K such that M is equal to 2 times K. That's the definition of even, okay? M squared even implies M even. That's a theorem we proved on Tuesday. M even implies there exists a K such that M is 2 times K. That's the definition of even. And now I put that back up in my formula, and I get that 2 times N squared equals 2 times K squared. And that implies that N squared equals 2 times K squared. Okay, so 4K squared, I cancel the 2's. So N squared is even. Question? M and, oh, well, these are, square root of 2 is positive, so it doesn't matter. Okay? So I'm working in the integers, but I've got M and N, they're natural numbers, so they're fine. That's not a problem. So 2N squared equals 2K squared. So N squared is even, and hence N is even. Whoops. This implies N squared even, which implies N even. Okay, so what's the problem here? They have no common factors, but they're both even numbers. Okay, so we've just shown conclusion, M and N have a common factor. Namely 2. So conclusion, not R2 is true. Okay? So this is our contradiction. We have a contradiction. R2 and not R2. R2 was the R1, sorry. Yeah, R1. If I looked at my notes, but that would be no fun. I wouldn't do that. Okay. R1, thank you. It was very, very subtly done. I appreciate that. R1. So R1 is, not R1 is true. We had R1 is true, so that's a contradiction. Okay, so not P has to be false, so P has to be true. Okay, so conclusion, not P is false, and thus P is true. Oh my gosh, okay. I mean, it's just so brilliantly simple. It's not my proof, it's Euclid's, okay. It survived for 2,000 and something years, but you show that there exist numbers that cannot be written as rational numbers. So there's and they call those irrationals, illogical, crazy numbers, okay? So crazy numbers exist. Question?
The statement where we said root 2 is rational further down below. If root 2 is rational, then there is m and n belongs to natural numbers such that so. I was just wondering if it would be more logical if we said m and n belong to whole numbers and m and n don't belong or not equal to 0.
That would be even better, because then I would have, so the question was, instead of putting n, I put z, and then I do my n not equal to 0. That would have been the better application of the definition. So that's better. Yep. Well, because I did natural numbers, I got lucky.
All right. So when I'm saying like when you're doing integers,
Then
whole numbers, then m should we have to just write n not equal to 0 or m and n not equal to 0?
just the denominator.
All right.
That's all you need. Just the denominator. Question?
Has anyone gone through the process of proving rational numbers using the proof method?
No clue. I assume there's many different proof methods, but I think any proof that can be done by contradiction can be rewritten without it, but it may be 20 times longer or something, but I don't know. Yeah. Okay, so this is a method that often makes proofs easier, shorter, and they're more fun, and you shouldn't fear them. Now, what I want to point out is this. Relation to the contrapositive. Okay, so P implies Q if and only if not Q implies not P. That's the contrapositive, okay? In another very common method of contradiction, we do the following. Okay. We assume P and not Q true Okay, so this is our statement now. It's a compound statement. So this is the P that we had before, but it's now a P, or P is now a P prime and a Q prime, if you wish. P and not Q. So we assume the hypotheses, but the conclusion is false. If we can show that this is false, then P and Q have to be true, okay? So, and seek to derive a contradiction. This gives us not P and not Q is true. Okay, you're going like, that's okay. So now what I want to do is go through something called a truth table. And we're going to build up the truth table for this, and then the light bulbs will start going on. Okay, so if you're confused right now, absolutely normal. If you're not confused right now, it means you've already had a really good course of logic and I'm boring you to death. Okay, so this is a proof with only two cases. You're liking this or you're not. Okay, so truth tables. Bingo. Oh yeah. Bing. Boom. Okay, sorry for the eye test, okay? Horrible. But this is the truth table for the not operation. P can be either true or false, and then we fill out not P. So P is true, not P is false. If P is false, not P is true. Okay? So this is in the handouts that I posted. So this is truth table for not. Or not. Bingo. Let me do another one. Oh, like this. So this is the truth table for the AND operation. You just write down P and Q, it can be true or false, and then this gives you the other set of combinations, okay? And then you just do the AND. If P and Q are both true, then the AND is true. If one of them is false, they're false, and if both of them are false, it's false. That's what the truth table is. You put down your logical elements, and then you put your logical elements, and then you put down the statement, and then you fill out this. So this is the part you would do. Now, since you guys are really clever, let's do the truth table for P implies Q.
Or if we seem to have a
Okay. P, Q, P implies Q. So true, true, false. Whoops, I have too many things. True, false, true, false. And that's a do not care, okay? Okay? So if P is true and Q is true, what is P implies Q? True. Okay. If P is true and Q is false, P implies Q is? That's obvious. Okay. If P is false and Q happens to be true, what goes here? I hear trues.
I think it would be true or false.
This could be true or false?
Yeah.
Okay.
The statement is not.
P equals 100% on final exam. Q equals passing grade. You know, maybe you got 0 on the midterm. Okay? So let's suppose you get 100% on the final. I say, I'm going to give you at least a B minus. You pass the course, okay? So that's the statement. So if you get a 99 on the final and I don't give you a passing grade, is this statement false? No. Okay. Now, if you get a 99 and I'm still sweet and I do give you a passing grade, is the statement false? Still true, okay? Okay, so this is what drives people crazy who haven't had a logic course before. Now we're going to do the truth table for the not P and not Q, the proof by contradiction. And what I'm going to show you is that it is much easier, okay? So now, let's do contradiction. So let's see if I can get this. I'm going to need a P, I'm going to need a Q, I'm going to need let's see, I want to do not Q, I want to do P and not Q, and I want to do not P and not Q. Okay. Bingo, let's see. True, true, false, false, true, false, true, false. Okay? Bingo. Okay, so we're just going to fill these things out, and hopefully that's going to be really quick, right? Because false, true, false, true. False, true, false, true. Now I do P and not Q, so I get false, true, false, false. Right, I'm just doing the and, false, true, false, false. Let you catch up. Well, maybe. You see what's going to happen in this next column? Okay, what's the not of P and not Q? True, false, true, true. Was that hard? No, that's super easy, right? There is no problem filling out that truth table. Now, which truth table does it look like? It's the same as P implies Q. So this one you have all this problem with. You say, oh, I love P implies Q. I really like it, okay? This proof by contradiction, man, that just drives me crazy. I just can't do it. No, there's the truth table. It's trivial, okay? That one's trivial. This one is takes some playing around with standing on your head and rubbing your belly and talking about 100% and stuff like that. There are other examples in the posted notes, okay? So this is the tool we have now, okay? Or tools. P implies Q. We know that's equivalent to not Q implies not P. But it's also equivalent to not P and not Q, okay? So, when you want to show P implies Q, it's up to you to do the contrapositive or a proof by contradiction. Either one, any one of the three. So this is, direct, contrapositive, and contradiction. It's up to you, Am I going to score, passing the ball to my friend who's a perfect shot? Me taking my best shot, whatever. You just got to decide what play you're going to run. The direct, the contrapositive, the contradiction. And it depends upon your skills, the problem at hand, etc. So those are all logically equivalent. And they're at your disposition. Questions about contradiction now? Does it seem a little bit better? Just a tiny bit better? Okay. Questions? We're going to do supremums, maximums, and because it's all written up very beautifully, I'm just going to hit a few highlights, okay? Okay, so we're going to focus on supremum versus a maximum. And it's one subtle little difference, and it makes a very important difference. So let A here be any subset of the reals. What do I mean by the maximum of A? The maximum of A has to be an element of A, first of all. And this is the key part. A maximum must belong to the set. So make that note. Max of a set must belong to the set. That's by definition. Because I think the rest of it, you don't have to memorize. Okay, it's the biggest element in the set, so if I take any other element in the set, that element has to be smaller than or equal to it. Okay, that part is, if you understand the word maximum, then that part follows. Okay, so if X is any other element of A, it is less than or equal to B. That means B is a maximum. But what the key part is that it has to be an element of A. And so if A is all real numbers between 0 and 1, what is its maximum? See, it says here it doesn't have one, okay? But, you know, it has to be an element. Oh, 0.99, is that the maximum? Well, 0.991 is bigger, okay? So let's go 9999, is that the maximum? No, we had another digit, it's still bigger, okay? Is 1 the maximum? And that's the mistake you can easily make. 1 is not the maximum because 1 is not an element of A, okay? That's the only point I want to make on maximum. Okay, so later on in the course, we're going to be doing optimization problems in the sense of how can I take this set of data and best approximate it by a function. So we're going to minimize an error. So we're going to talk about minimums, okay? But let's pretend we're maximizing something else, okay? So I write down my problem, x star equals the max of this. The problem with that is, I don't know if the maximum exists. So if I can give you an object where I can say x star is something else, and that will be the supremum, or that something else instead of minimum will be infimum, and that thing always exists, then what I'm writing down makes sense. And then in my proof, I can go out and, or my theorem, I can discuss existence and how you characterize it, how you would compute it numerically. But I define this object and it always exists. That's super cool. So the supremum of this set will be 1. Okay? We will define it to be, it's the least upper bound. It's any number in the reals that is an upper bound, and it's the smallest of all of those. Okay? So an element is an upper bound if everything in A is less than it. Okay. 2 is an upper bound. Not a very tight one, though. 7 is an upper bound. 1.1 is an upper bound. 1.01 is an upper bound, but 1 is the smallest upper bound. And that has a definition. It's called the supremum of the set. The smallest upper bound. So the upper bound does not have to be an element of the set. It's any element of R. And so upper bounds, there's a whole infinite number of them, and you take the smallest of those, and that's called a supremum. So, upper bound does not have to belong to the set. Smallest element of all the upper bounds always exists and is called the supremum. Whoops. So when you go through this handout, this is the key thing. The max must belong to the set. The upper bound does not have to. It is a property of the real numbers that every bounded set has a least upper bound. Proving that is super, 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 super hard. It's equivalent to the axiom of choice. Okay, it's really, really, really high-level math. I can't do it, okay? I don't know the proof, but it's true. So as an engineer, I use that. And then supremum is too long to write. We just call it the soup. And it's pronounced like a bowl of soup. Soup. Okay? And you write soup or soup. So I think the concepts are fairly straightforward, but you need to go through and read the handout. And as long as you notice max have to be in the sets, but supremums don't, that's the whole difference. Minimums have to be in the set, infimums do not. Okay. So once again, here's a bounded set. It has a supremum, it's 1. Here is a bounded set. Its supremum is in the set, so it's also equal to a max. If the supremum is in the set, then it's a max. It's not hard to figure out. Okay. So this. It's a special property of real numbers, okay? It's not true for the rational numbers, etc. So, and then the opposite of maximum is minimum. Minimum must be in the set. Then you talk about lower bounds instead of upper bounds, and then the biggest lower bound, that's the infimum. If we go back to here, a lower bound is minus 12. Another lower bound is minus 4. 0 is also a lower bound. It's not an element of the set. 0 is an infimum, but it's not a minimum. The set does not have a minimum element. So we will need this a little bit later on. It's not a big deal right now, but it's vocabulary. Okay? The min of a set may not exist. Okay. The infimum will. Okay, now. How's that for a question? What is infinity? Okay, it's simply a symbol. The real numbers would not themselves, they're not a bounded set. But it's still nice to be able to talk about their sup and their inf, the infimum. So infinity is simply a symbol. Infinity satisfies for every x in the reals, x is less than infinity. Minus infinity satisfies for every x in the reals. Oh, that was part of my question thing. Minus infinity is less than x. So one often works with something called the extended real numbers, where you take the union over all real numbers, you add in infinity, and you add in minus infinity. You never really write the plus, but it's just to be extra super clear, okay? So this is the sup over all real numbers, and this is the infimum over all real numbers, by convention. You know, what is 3 to power 0? 1, by convention, okay? This is a convention. Please. Can I say that infinity is the supremum of the reals as the definition? Was that the question? Well, you have to first define, there's no proof that says the real numbers have an upper bound, because here's the definition of an upper bound, okay? So we took a subset of the reals, so the reals are a subset of the reals, just to answer the question. And then, where's my, there we go. And then we defined here an element of the reals is an upper bound if x is less than or equal to that for every x. And so there is no element of the reals that satisfies this. Just add 1 to it and it would fail. So the problem is we couldn't define, so if the sup is the least upper bound, the problem is the reals do not have an upper bound. There's none. So you can't do that as the definition. So this is the end around, okay? This is the trick. Good question. But for you on an exam, I'm happy with that definition, okay? I'm not worried about that level of precision. If you go over to the math department, it's great because they make you get into that level of precision. Cool. Others? Infinity. Yay. So, back to our notes. Nope, this one. Okay. See handout. On max and sup and min and inf. Max and min must be an element of the set. While sup and inf do not have to satisfy this restriction, okay? So if you just take this idea, it will get you to the essence of max versus sup, min versus infimum, inf. Ding, ding, ding. Questions? Is that too fast? Would you have wanted to write that handout out every line by line? This was a little bit better. Okay, good. Okay, so now I want to practice negating statements. Just use the rest of our time here. Why do we want to practice negating a statement? Well, if we want to do P implies Q, we might want to do not Q implies not P, or might want to do not P of P and not Q. Okay, there's all sorts of nots showing up in there. We're negating things all the time in our proof technique. So a little practice at that. So we'll start with the most trivial, and then we'll build up to compound things where there's lots of quantifiers and things like that. So, statement P, x is greater than 0. What is not P? X less than or equal. Yay, that was not so hard, okay? P. For every x in the reals, f of x is greater than 0. What is not p? Okay, so some of you have had practice with this. For the rest of you, I'm going to show you a long way to do it that you should do 3 or 4 times, and then you won't do that anymore, okay? So, the not of p is not for all x in R, f of x is bigger than 0. So step 1, express it in written words. If you want to make the graders super happy, use a native tongue that is not English, okay? Write this out, okay, in language, not symbols. Well, language is symbols, but not math symbols, okay? So, now, this is if and only if what, okay? So not p. If it's not true that for every x, for all of these x's, this is positive, you have for some x, this is false. Okay? So, then not f of x bigger than 0. Now, if you immediately replace this with f of x less than or equal to 0 instead of saying not, you know, that's like not writing down every little step on doing the addition or multiplication of 2 numbers, okay? So, for some x in R, f of x is in fact not positive. And the symbol for some is this backwards E. Okay. There exists x in the reals such that f of x is not positive, okay? It's less than or equal to 0. Okay, so this was now compound. There were 2 terms here. When I just had x bigger than 0 and I negated that, nobody had any problems. So this one, notice the pattern though. Okay? Pattern. Not of this goes to there exist. Okay? If it's not true for everything, then there must be some element that makes it false. Okay? That's the pattern. Not true for everything, there is some element that makes it false. Okay? So, not true for every x in R, then there exists an x that makes that statement false. F of x greater than 0 is false when f of x is less than or equal to 0. Okay. Whoops. Also true, not there exist goes to every. There does not exist this such that something is true means for everything it is false. Okay. So let's do another one. Okay. Another example. Let y be in the reals. And then P is this. For every X in the reals, no, sorry, it's a delta, sorry. I should look at the right example. My apologies. For every delta positive, there exists an X in the rational numbers such that X approximates Y with an error that is no bigger than delta. It even could be smaller than delta. So here's my statement. It's really essentially a defining thing of the reals, okay? So any real number can be approximated arbitrarily closely by a rational number. Let's do not P. Whoops. Not for all X. No wonder, I'm looking at the wrong page. No wonder. For all delta greater than 0, there exists X in the rational numbers such that the difference between X and Y is smaller than delta. So the not of this is, well, it's not true for every delta, so for some delta, whatever follows is false. Okay? The not of P is for some delta greater than 0, then I'll just write it out. Not there exist X in Q such that absolute value X minus Y is less than delta. It is not true for all delta greater than 0 that the following approximation statement holds. Hence, for some delta positive, this approximation is false. Okay? That's the pattern. So not P. For some delta greater than 0, there exists a delta greater than 0. Okay. Not, okay, there exists X in Q, so you could say there does not exist X in Q. It's possible to say that. There does not exist X in Q such that absolute value of X minus Y is less than delta. Excuse me, I said not exist. And then the not exist, if there is no X such that this is true, that means for every X in here, this is false. And that's the better way to write it. There exists delta greater than 0 such that for every X in Q, absolute value of X minus Y is bigger than or equal to delta. Okay. this is equivalent to does not exist x in q such that it's less than delta. Okay, so remark. It's better to avoid this thing and this. But they're legal. You can do it, okay? It's okay. One more example. You want your full time? Yep. 4 minutes. One more. Oh, you guys are fired up. Okay. Pete, for every y in R, for every delta greater than 0, there exists an x in the rationals such that absolute value of x minus y is less than delta. Oh my gosh, I've got 1, 2, 3 quantifier symbols. Negate it, okay? That was a command form of the word, negate it. Do it. I'll give you 1 minute, and then we'll just do it. More seconds. Okay, solution. You can do these recursively. The not of for every is there exists. Okay? So, not. There exists y in R such that not, okay? For every delta greater than 0, there exists x in q such that absolute value of x minus y is less than delta. Okay? For every not, there exists, and then you do the not of everything that follows. That's what I mean by recursive. Now, we just did this one, okay? Conclusion, not P, there exists y in R such that there exists delta greater than 0 such that for every x minus for every y, this such that for every x in q, absolute value of x minus y is greater than or equal to delta. Okay? That's from the one up above. Okay. Oh, thank you. It was something trivial. I thought I just totally messed it up. I feel so vulnerable up here, okay? It was so much better when these lectures were not filmed, okay? I just wrote them on the board. I didn't feel vulnerable at all because I could claim it never happened. And unless you guys were sitting there with your cell phones, which you didn't have when I started teaching, there was no proof. It's my word against yours. Okay, I hope you've enjoyed the second lecture. We'll start linear algebra. So those of you who are in EECS 560, which is ME 564, which is Aerospace 550, we've got 2 to 3 weeks that are very similar. It's in that announcement. Sorry for you guys, okay? Final thing, if you follow these lectures via recordings and you don't come to class, I do not hold it against you. Please come to office hours anyway and ask questions, get to know me, do whatever works for you. Okay? I'm here, I'm enthusiastic. I like you to come, but I don't require it, okay? Very good. Takes about, I upload the documents as soon as the